Hi, my name is Jeff Sachs. I, along with Anay, Mehrotra, and Elisa, Celis, conducted this research at Yale University. Numerous studies have found that algorithms functioning in our daily lives can be biased, and that these biases can cause harms. These observations have led to a great deal of exploratory work studying fairness in socio-technical systems from a computational perspective. Studying fairness from a computational perspective is a growing field, and from it a wide array of fairness metrics have been formulated to evaluate fairness. Why do we need the fairness metrics? One good reason is that if we want computer models to be able to ensure fairness and perform well, we need good metrics that quantify how fair outcomes are. There are broadly two types of fairness metrics, group and individual metrics. In this research, we focus on group fairness metrics. The goal of a group fairness metric is to evaluate how equitably groups are represented in a given outcome, or how evenly resources are allocated across groups. Examples of settings for this research include search engines, online advertising, hiring, and credit lending. There are many notions of group fairness across disciplines. Many of them function by measuring the similarity of particular outcomes across groups. With this, metrics typically have two parts: an outcome measure, which measures outcomes received by each group, and a similarity measure, which measures the similarity of outcomes. Statistical rate, for example, is the ratio of the worst outcome to the best outcome. In computational fairness research, a plethora of metrics have been derived to measure fairness with respect to a set of outcomes. Most group fairness metrics, however, do not consider the underlying network connecting individuals. By this we mean that fairness metrics typically assume individuals are isolated. They often measure the similarity of aggregate outcomes, such as how many individuals were hired from each group. For many contexts, however, we wonder, is the network structure connecting individuals important to evaluating fairness between groups? In social network analysis, a great deal of research has been devoted to deriving measures that relate the structure of relationships in a network to structural advantages and disadvantages with respect to accessing resources. The centrality of individuals, for instance, and their reach to others in a network shape their ability to access and control the dispersal of resources. The central principle that underpins this research is that individuals are socially situated. Individuals will form social ties like marriages, friendships, work associations, along leading socioeconomic dimensions such as geographic location, income, occupational status, and educational attainment. This phenomenon is often known as homophily. In some cases, protected attributes used to define groups, such as race, can correlate strongly with socioeconomic status, which suggests that it can also correlate strongly with particular network features conducive to accessing resources in networks. This suggests that networks can have a non-trivial impact on the evaluation of fairness. Consider, for example, needing to select a few individuals as leaders in a network. The individuals of the network may have different protected attributes, and in an effort to be fair, we may attempt to represent each protected group equally, such that each group has the same proportion of individuals selected as leaders. The underlying network, however, might reveal that centrality clusters along certain social characteristics, meaning leaders in some groups have a higher centrality than others. In this case, we believe that more central leaders will have more social influence, and that influence will be more concentrated in some groups over others. With this, even though each group is proportionally represented, selecting leaders in this way gives advantages to some groups and not others. But the question is, how can we measure such biases on networks? In our research, we introduced templates for group fairness metrics that account for network structure. We have formulated two broad types of metrics that measure distinct yet complementary forms of bias in networks. The first type are intra-network fairness metrics, which evaluate how access to others in the network is distributed across groups. These metrics generalize common group fairness metrics to account for the structural advantage occupied by different groups in a network. The second type are intergroup fairness metrics, which evaluate how equitably groups distribute their interactions across other groups. Intra-network metrics generalize non-network fairness metrics. They are composed of an outcome measure and a similarity measure like traditional non-network fairness metrics. The difference is that while each of these parts of the non-network fairness metrics are independent of the network edges, the outcome measure of an intra-network metric is a function of the edges. In general, given different contexts, you can pick one of many network measures to define the outcome measure, and one of many similarity measures to evaluate bias in the outcome. Importantly, intra-network fairness metrics reduce to non-network fairness metrics on the complete graph. Now let's look at a toy example. In the figure on the left, each group has the same number of outgoing edges, so the statistical rate is 1. In the figure on the right, the green group has more outgoing edges than yellow or blue. As part of our empirical work, we compared the intra-network fairness metric to a traditional non-network fairness metric. Using network data on several Ugandan villages in which a network survey was conducted, we looked at male and female villagers who were selected as leaders. We then considered the underlying network and looked at the distribution of leaders who were identified as problem solvers in the network survey. Surveyed villagers identified a person as a problem solver if they saw them as someone they would go to for help. We therefore interpreted problem solver ties as being more influential in the affairs of villagers. For our analysis, we used the total in degree as the outcome measure for the intra-network metric. The non-network fairness metric shows that the representation of leadership among men and women to be relatively fair. The intra-network metric, on the other hand, suggests that a non-trivial amount of influence is accounted for in the relationship structure of the network, giving male leaders, in this case, a great deal more influence. The underlying network also specifies how different groups interact with each other. In several contexts, bias can manifest in how individuals in one group interact with those in other groups. Intergroup fairness metrics capture these biases. Unlike intra-network metrics, intergroup metrics do not have a natural non-network analog. This is because intergroup metrics deal with interactions between groups which are absent without a network. Like an intra-network metric, however, an intergroup fairness metric can be divided into two parts, an interaction measure and a similarity measure. An interaction measure is a network measure that evaluates how groups distribute their ties across other groups. Here we have a simple toy example again. Using total outgoing edges as our interaction measure, the figure on the left evaluates as fair because each group sends an equal number of edges to each other group. They are not favoring one group over another. This does not hold for the figure on the right. For our empirical example of this metric, we compared an intergroup metric to an intra-network metric. We used publicly available network data consisting of friendship ties among high school students. Here we compared friendship ties between different racial groups. For the intergroup metric, we considered the intergroup outdegree as the interaction measure, which is defined as the average number of edges from a node in group I to a node in group J. The chord diagram on the right visualizes the distribution of friendship ties between racial groups. Here, color specifies each group and the edges indicate the direction of the outgoing ties. The width of the chords indicates the volume of ties sent between groups. Using an intra-network metric, we observe that each group interacts with a similar number of individuals. In contrast, the intergroup metric reveals that each group is not interacting with other groups equally. In conclusion, one of our major limitations is that we do not address what is fair in a specific context. But before using the proposed metrics to evaluate fairness, this question must be answered. For future work, we want to extend these fairness metrics into predictive processes. Finally, we see several domains in which network-based fairness metrics can be used. These include information diffusion, representation in workplaces, events, and schools, and competitive pricing strategies targeting influential customers. Thank you.